Okay, so where we left off last time was sort of reviewing our rules for nomenclature. Every time we name a molecule, we got these same 4 steps that we're going to do. We're going to find our parent chain, our longest continuous set of carbons. We're then going to find and label all of our substituents. From there, we're going to number our parent chain, and then we're going to put it all together, put our name together. Okay? We started out with one fairly easy example. Let's do another one here. Okay? We'll sort of add to this list of rules as we introduce new complications here. All right, we did an example with 1 substituent. So now let's go ahead and do an example here that has 2 substituents. Step 1, we got to find that parent chain. What is the longest continuous set of carbons in that molecule? How many carbons are in our parent chain for this one? 5, right? So 1, 2, 3, 4, 5. That's my longest continuous set of carbons in my parent chain. Okay? We're going to find and label our substituents. This 1 carbon group right here is a methyl group. I got another substituent over here, and this one's 2 carbons. So what would this one be? An ethyl group. Step 3, we got to number our parent chain. We can always number our parent chain 2 ways. All right, 1, 2, 3, 4, 5, or I'll go the other way. And which one's going to be correct, the red or the blue numbering scheme here? The red, right? Because I want the smallest possible number in my name. Okay. All right, cool. So now we're all step 1 through 3. Now we got to get to this part where we assemble our name, okay? And importantly, now I have more than just 1 substituent. So another rule we need to add to our assemble the name here. We always go locant, then the substituent followed by the parent. But if we have multiple substituents, how do we organize that in our name? Alphabetical order, all right? So multiple substituents. We need to organize in alphabetical order. All right, so since F comes before meth in the alphabet, this would be 3-ethyl, 2-methyl pentane. Okay. Remember our alkyl substituents, only carbons and hydrogens. We stick this YL onto the end, right? So that's why it's a methyl and an ethyl group, all right? The other category of substituents that we want to know is our halogens, all right? So let's do an example here. This example will introduce 2 new rules. I should have had you fill in the lone pairs. Remember, our halogens are a 1 bond, 3 lone pair kind of atom. Okay. You would have talked about the chemistry of these alkyl halides before. We can kind of think of them as a functional group. They undergo certain reactions, but from a nomenclature standpoint, we don't treat them as a functional group. We treat them as substituents. So they have their names. They'll go at the front half of a name. They're not a back half of the name kind of functional group, right? They're considered a substituent for nomenclature purposes. So We got to name these things here. We said alkyl groups have that YL ending. If we just go down the line for our halogens, F is a fluoro group. Cl is a chloro group. Br is a bromo group. And iodine is an iodo group. All right, so these halogens are treated like substituents. Like our alkyl substituents, we learned how to name these. Our halogens, these are how we name them as our substituents. Fluoro, chloro, bromo, and iodo. Okay? Cool. So, super creative today. How many carbons are in our parent chain? 5 again. All right, step 2, we're going to find and name our substituents as we just reviewed here. This is a bromo group. And this is a chloro group. Okay, so now I need to number my parent chain. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right. Remember when we talked about our numbering scheme, we're going to number such that we get the lowest possible number in our name. But if we look, we got a problem here. In my blue numbering scheme, we got a 2 and a 4 in the name. And in my red numbering scheme, I got a 2 and a 4 in my name. So based on the rule that we covered, the lowest number in the name thing, we are at a tie here, okay? So if and only if you get to a tie, how do you break that tie? Alphabetical order, okay? Now, one thing that people get confused about is they start always putting things in alphabetical order. No, no, no. It is only in a situation like this where both of your numbering schemes gives you an exact tie. You break that tie with alphabetical order. Don't default to alphabetical order. Okay? But we're going to say for our numbering scheme, lowest number in the name, if there's a tie, then we break with alphabetical order. All right, so if I'm going to break this tie with alphabetical order, I'm going to use the blue numbering scheme. The bromo will get the lower number. Again, when I assemble, I always assemble in alphabetical order. So this would be 2 bromo, 4 chloro, pentane. Okay. All right, so now we're going to talk about our first functional group here. This molecule contains a double bond, so what's our functional group? Alkene. All right, so importantly, if we have an alkene, we need to use a different suffix for our parent chain. Alkanes end in ane. Alkenes end in ene. And then our triple bond alkynes would end in yne. Right? And when we find our largest set of carbons, our continuous set of carbons in our parent chain, we're going to add to it that it must contain that functional group. All right, the longest continual set of carbons that contains that double bond. That has to be a part of my parent chain. You can't have the double bond as a substituent sticking off of your parent chain. It has to be included in the parent chain of your molecule. Okay, so everybody take a second, try to do steps 1 and 2 here. Find your parent chain, find and name any substituents, and then we'll talk about numbering our parent chain. All right, 1, 2, 3, 4, 5, 6 carbons in my parent chain. Do I have any substituents? That fluoro group. I'm going to number my parent chain 1, 2, 3, 4, 5, 6. Go the other way. Okay. So now, when we're picking our numbering scheme, now we have a molecule that has a functional group in there, that has that double bond. Okay. When it comes to our numbering scheme, we prioritize functional groups. Meaning the only thing I'm going to pay attention to when I pick my numbering scheme is the location of that double bond. Functional groups get priority, meaning you ignore everything else that's going on. Okay? So when we're numbering our parent chain, we're going to keep in mind that functional groups have this magic word, priority. So if we were looking at the fluoro group, we would be tempted to pick the blue numbering scheme, but I'm not going to pay attention to anything other than my functional group in that molecule, where that double bond is located. Okay? This double bond is located, so i.e. I'm going to pick my red numbering scheme. Okay? The double bond is located between carbons 2 and 3. We reference that with the lower of those two numbers. All right? So that means I'm going to label my double bond as being on carbon 2, and it's implied it's between carbons 2 and 3. All right? So when I put my name together, I need to include that substituent out front. So this would be 6-fluoro. I also have to include the location of that double bond, 2-hexene. Okay? A perfectly equivalent way to do that is to actually put the number directly in front of the ending itself. So you could have also said 6-fluoro hex 2-ene. Either one of those are perfectly fine. Truthfully, it looks a little weird to throw it in the back half of the name. We'll sort of talk about molecules that have multiple functional groups, and then you have to build it into the back half of the name, but we'll see an example of that as we go on. We're not going to cover that here. Okay? Cool. All right, cool. So that catches us up to date on our nomenclature rules. We have our parent chain. At this point, we should know alkanes, alkenes, and alkynes. Alkynes are just triple bonded compounds, okay? In terms of our substituents, we should be able to label alkyl substituents as well as the halogens, the fluoro, chloro, bromo, and iodo group. All right, when we're numbering our parent chain, we always want to include the lowest number in the name. If there's a tie, we break that tie with alphabetical order. But then importantly, if we have one of these molecules with a functional group, an alkene or an alkyne, we prioritize that functional group when we label our molecule, when we give our numbering scheme. All right? Then at the end, when you assemble everything together, you put all of your substituents in alphabetical order, right? And no spaces in the name. You just ram everything together. Cool? All right, crash course on nomenclature. So now we're going to move on to electron pushing arrows here. Okay? We're going to look at an example reaction here, and for the sake of illustrating this, we're going to pick a fairly simple reaction, an acid-base reaction. All right, this is a type of reaction that you study in like just about every chemistry course up until this point, right? You've covered it a little bit in Gen Chem, covered it a little bit more in depth in 1B. You go even more in depth in organic chemistry, right? So this is a good example reaction here. We're going to just pick kind of simple acids and bases. And of course, it's all about the structure. So I'm not just going to write the chemical formula, I'm going to write out my structures for these molecules. Since they're so teeny tiny, we're going to use Lewis structures. All right, so we're going to use hydrochloric acid and sodium hydroxide, really just the hydroxide molecule. All right. I have left off my lone pairs and my formal charges here. All right, before we move on, I want everybody to take a second, and I put in the lone pairs on the chloride because I didn't think beforehand, but I want everybody to take a second and fill in any missing lone pairs and formal charges that we see in our structures here. Okay, remember we talked about those bonding patterns and formal charges last class. We made a little cheat sheet that you can reference if you're stuck. All right, so we say oxygen likes to have 2 bonds and 2 lone pairs. So if I see those 2 bonds, I know there are 2 lone pairs on that oxygen. Okay. What about over here where it only has 1 bond? How many lone pairs does it have to have? 3. And if it has 1 bond and 3 lone pairs, what's the charge? Negative. Okay. And then a chloride all by itself. All right, we didn't make a cheat sheet for halogens, but it follows the same pattern. A halogen likes to have 1 bond and 3 lone pairs. If I take away that bond and replace it with a lone pair, now I have the chloride ion. Okay. Another thing that you could have convinced yourself that that chloride ion has to have a negative charge is because charges have to be conserved. If I have a net charge over here of -1, I better have a net charge over here of -1 as well, right? We have this conservation of charges. Charges are notoriously difficult to keep track of, so having little tricks like that to double check are really helpful. All right, so we have this acid-base reaction. My acid, remember, is a proton donor, so that's this guy right here, the hydrochloric acid. It's even built into the name. That's a proton donor. It gets rid of that hydrogen. The base then accepts that proton. That's what a base is a proton acceptor, right? So again, this is a simple acid-base reaction where my hydrogen is changing bonds from being bound to the chloride to now being bound to the oxygen, okay? And what we want to be able to do is we want to be able to put in our electron pushing arrows, all right? So, name of the game that we're going to play here is what I like to call the spot the difference game. Okay? Chemical reactions are all about making and breaking bonds. And what are bonds made of? What are covalent bonds made of? Which one of our subatomic particles is being shared in this covalent bond here? Protons, neutrons, or electrons? Electrons, okay. Whew. Electrons are what make up a chemical bond, right? So when we talk about a chemical reaction, when we talk about making and breaking bonds, we're really reshuffling around the electrons here, right? That's what's happening in a chemical reaction. Other than that very specific type of chemical reaction that you learned about in Chem 1B, nuclear reactions that take place within the nucleus of an atom, that's a really special subset of chemistry, right? 99.999% of the time you're talking about chemical reactions, you're talking about making and breaking chemical bonds, which consist of electrons, right? And what we want to do is show how our electrons are moving in a reaction. That is the basis of these electron pushing arrows. All right, so first we're going to play the spot the difference game. I want to say we would need to be able to find what bonds are being broken, what new bonds are being formed. We need to know what lone pairs we're losing. And what new lone pairs we see. All right, so take a second. I'm going to color coordinate these. You can just label them in your notes. All right, but we're going to keep track of what bonds are being broken, what new bonds are being formed, where we see lone pairs on the left that are no longer there on the right, and vice versa. What new lone pairs do we see on our product side? Okay, so everybody take a second. Given our reaction here, play the spot the difference game. Okay, do we see any bonds that get broken in this chemical reaction? Which one? The hydrogen and the chlorine bond. This one right here is going to be broken in my chemical reaction. And what new bond is formed in this chemical reaction? The hydrogen-oxygen bond. Boom, that wasn't there on the left-hand side. Now we see it on the right-hand side, okay? But equally as important to focusing on the bonds, we also got to focus on our lone pairs. Do we see any lone pairs on the left-hand side that are no longer there on the right-hand side? Lone pairs that get removed in this reaction. Which one? Oxygen. On the oxygen, right? Oxygen on the left-hand side has three lone pairs. On the right-hand side, it only has two. Okay? And what about new lone pairs? Are there any atoms that have a new lone pair on the right-hand side that weren't there on the left-hand side? The chlorine. Cool. So in this reaction here, we have this bond between hydrogen and chlorine being broken, and then the chlorine now accepts a new pair of electrons, becoming a chloride. And for the hydroxide ion, there was a lone pair on that oxygen, but now there's this new oxygen-hydrogen bond, okay? And what we're going to do is we're going to show the movement of these electrons using these electron-pushing arrows. So let's lay down some rules real quick for drawing electron-pushing arrows. Okay, So the tail of these electron pushing arrows must begin at a pair of electrons, either a lone pair or a bonding pair, but it has to start at a pair of electrons. The head of our arrow must point at the atom that's accepting that pair of electrons. Okay? All right, so we played the spot the difference game. I'm going to rewrite this so it doesn't get too confusing here. Again, we said that this bond right here, this hydrogen-chlorine bond, was broken. Well, electrons don't just disappear into thin air. All right, that pair of electrons went somewhere. Where did that pair of electrons go in this reaction? Right, so if we look, we have chlorine here with 3 lone pairs, and on our product side, it has 4 lone pairs. Where did that extra pair of electrons come from? Well, it used to be that bonding pair between hydrogen and chlorine. Okay? That chloride ion is accepting that pair of electrons. So the way we draw that with our electron pushing arrows, again, the tail of the arrow is always at a pair of electrons. In this case, this bonding pair here. And the head of the arrow is always pointing at the atom that accepts that pair of electrons. Okay? So this would be our electron pushing arrow to break that bond. And this is one of these patterns we're going to see. Our electron pushing arrows, they could show us a bond breaking, as is the case in our example here. When a bond breaks, that pair of electrons has to go somewhere, so it goes from being a bonding pair to now just a lone pair. So bond breaking means a bonding pair becomes a lone pair. The tail of my arrow here is then sitting on that bond. And again, the head of the arrow is at the atom accepting that lone pair. Okay, so that's how we illustrate a bond breaking in organic chemistry. That pair of electrons has to go somewhere. It's going to become a lone pair. All right, when we played our spot the difference game, looking at the other pair of electrons here, we said that this oxygen had this pair of electrons on our left-hand side. And all of a sudden now that pair of electrons is gone. But what we do see, that lone pair of electrons is gone. And instead what we see is this new bond here. Well, where did that bonding pair of electrons come from? That used to be my lone pair. All right, so now we're going to do the exact opposite. Now we're going to turn a lone pair into a new chemical bond. All right, again, the base of my arrow always has to start at a pair of electrons. In this case, it's going to start at that lone pair. And the head of the arrow is going to go on the atom accepting that pair of electrons. In this case, it's that hydrogen atom, right? That's where my new bond is being formed. Okay? So the one arrow, let me actually move it to the top here so we don't get too confusing. This first arrow we said was a bond breaking arrow. Our new arrow that we just drew, this is a new category. This is now a bond formation arrow. Right? A new chemical bond, a new covalent bond is being formed. Okay, so we got a new pattern here. Now we have bond formation. Again, we see that bond formation is when a lone pair becomes a bonding pair. I'm going to use a simple example here. Let's do a different. We're going to do a bromide ion. This will react with our carbocation, for example, and we will form a new bond. Our electron pushing arrow is going to start at that lone pair. And again, it's going to become a bonding pair. So the tail of my arrow is on a lone pair. And again, the head of the arrow is always at the atom, accepting, in this case, that new bond. Okay? Cool. All right, so let's see if we can just sort of fill in our electron pushing arrows. I'm going to put down another reaction. I'll show you the reactant side and the product side, and you're going to put in these arrows. How do we get from point A to point B on this one? Okay? All right, you want to start out by playing that spot the difference game. What bonds are being broken? What new bonds are being formed? What's happening with our lone pairs, right? And then you will draw in your electron pushing arrows. All right, do we have any new bonds that are being formed in this reaction? Which one? Nitrogen, hydrogen. And remember, when we have these bond formation arrows, we're going to start at a lone pair, and we need to end at the atom that is accepting that new bond, right? So my nitrogen lone pair is going to reach out and grab that proton. Am I done? No, because I also have a bond that's being broken in this reaction, right? What bond is being broken? The hydrogen-oxygen bond. And where is this lone pair going to go? It's going to become, I'm sorry, where's that bonding pair going to go? It's going to become a lone pair on my oxygen, right? So my oxygen is going, this hydrogen-oxygen bond is going to break, and oxygen will be the one to accept that lone pair. Okay, so again, we got our bond formation arrow. Whoops. And we have our bond breaking arrow. Again, just to emphasize, the tail of the arrow always at a pair of electrons, the head of the arrow always at an atom, right? The head of your arrow shouldn't be pointing at a pair of electrons, should be pointing at an atom that's accepting that pair of electrons. Okay, there's one more pattern that we're going to see. So we have bond breaking, we have bond formation. There's one more that we encounter quite often, and this is both things happening simultaneously. So this is bond breaking and formation all in one shot. Okay, we see this with a particular type of functional group, our pi bonds, so our alkenes and our alkynes. All right, so if we have, for example, an alkene, let's just use our other halogen. Okay. One of the reactions that you learned in the first semester is that an alkene will react with a hydrohalide to form an alkyl halide. These are what are called addition reactions. You add the hydrogen to one side and the iodo group to the other side of what was formerly your double bond. Okay. In the mechanism for this reaction here, the thing that is reaching out and grabbing that hydrogen is actually that pi bond pair of electrons, right? So the first step in your mechanism is this step here, okay? This represents both that pi bond being broken, that carbon-carbon pi bond breaking, but also a new bond forming between the hydrogen and that carbon, okay? So this bond breaking formation is a pi bond. Your arrow starts at a pi bond and it becomes a new bond. All right, I'm not quite done here. There's another step that I will have to put in, which is the breaking of that hydrogen iodine bond. All right, where do we think that pair of electrons is going to go? Okay, let me just show you. If you have two arrows pointing in the same direction, you're doing something wrong. Electrons will always flow in one direction. They'll never bunny ears together, okay? So that hydrogen isn't going to accept that pair of electrons, that halogen is. All right? So our intermediate here is that iodide ion. Iodine accepts that pair of electrons, becomes negatively charged. Okay? But importantly, when this pair of electrons breaks, when that pi bond breaks, let me just kind of illustrate, see if I can't. Okay, here's my pi bond pair of electrons here. Importantly, that pair of electrons is going to reach out and grab that hydrogen atom. All right, but so now I have this new carbon-hydrogen bond. I guess to be consistent with how I drew it over here, that pi bond reaches out and grabs that hydrogen. Okay, but just as importantly, that pair of electrons got snatched away from that carbon atom on the other side of that double bond, leaving it with a positive charge. All right, so when we have this bond-breaking bond formation, we will always have these carbocation intermediates as well. That pair of electrons got taken away from that neighboring carbon atom when that new bond was formed. All right, something that's kind of hard to see if you don't fill in your missing hydrogens. Right? If we filled in our hydrogens, we would see that there was only one on that carbon, leaving it with only 3 bonds over here. Okay? So then everybody take a second and finish off this mechanism. Get me to my product side. You should be able to fill in your electron pushing arrows on this intermediate step here. How do we get to the end? What type of arrow am I drawing? Bond breaking, bond formation, bond breaking and formation. Just formation. I'm going to start out at a lone pair and end at that carbon that's accepting that new bonding pair of electrons. Cool. All right, so these are these 3 patterns we're going to see over and over again for our electron pushing arrows. All right, let's just do one more example. Okay. We're going to discuss alcohols here in a bit. Okay, what we're going to see for one of our reactions of alcohols, right, they will react with these hydrohalides here. Okay, and the first step in this mechanism is this. Okay, so I need you to follow these electron pushing arrows and draw me my structure of my intermediate here. All right, let's try to label these, breaking or formation. This first one here, what do we have? Is this a bond breaking or a new bond that's forming? Forming, right? Starting at a lone pair and ending at an atom. This would be a bond formation arrow. What about the other one that's starting at a covalent bond? Breaking or formation? Breaking. Okay, great. So let's draw our newly formed bond. I guess I do want to put that right underneath. Okay, so here's my oxygen. It already had that one hydrogen on there. Now it's got a new bond to an additional hydrogen. How many lone pairs should this oxygen have with its 3 bonds? Only 1. And if it's got 3 bonds at 1 lone pair, what's the charge of that oxygen? Positive. Okay, so now we have this positively charged oxygen here. What else am I missing? That chloride ion, right? That chlorine accepted that pair of electrons, and so now I also have that chloride ion floating around. Okay? You could have again convinced yourself because of charge conservation, there had to have been something negatively charged there because my net charge has to equal 0, just like in my first step. All right, so paying attention to electrons and charges is sort of a notoriously difficult thing to do. All right, cool. So now you're going to put in the electron pushing arrows that would get me to this step here. Now I have 3 things floating around. I have a water molecule floating around. I have my organic compound with a positively charged carbocation, and I have my chloride ion is still present. All right, draw in your electron pushing arrows that will get you from A to B here. I guess I'll draw out the structure of water just to be good. All right. So for the sake of time, let me just go quickly here. Hopefully we could see that we're going to need a bond breaking arrow here. We got to break that carbon-oxygen bond. Where's that pair of electrons going to go? That becomes my new lone pair on my water molecule. Okay? So then just to finish off this reaction, we would have another arrow that starts at that lone pair and ends at that positively charged carbon. Is that a formation arrow or a breaking arrow? That'd be a bond formation, all right? So now we have our new product. We've converted our alcohol into this alkyl chloride, and now we have water floating around as well. Okay, and we didn't study this reaction, but again, the whole purpose is that if I'm putting arrows down, you should be able to follow those arrows. You should show me the next step in that mechanism. And likewise, if I give you a beginning and an end point, you should be able to draw in the arrows to connect those dots, right? To show me how those electrons moved. Those are our electron pushing arrows. Many reactions that we study, we will also study the mechanism for. Cool.